We are Team ELA, here to present our entry into the Dassault Systèmes Sustainable Aviation Competition 2020. Our team hails from the University of Bath and consists of 4 recent aerospace engineering graduates. My name is Owen Midder. I'm the competition team manager and systems engineering lead.
I'm Mark Glazier, the design lead for this project.
I'm Cameron Jones, the lead simulation engineer and supply chain manager.
I'm Nick Daggett, the propulsion engineer.
At the University of Bath, the ELA, or Electric Light Aircraft team, have been designing solutions for the future of air travel since 2016. Some of our previous contributions have included an all-electric commuter aircraft with 9 seats, developing a strategy for generative design for additive manufacture, and volumetric analysis of propulsion unit egress mainstream interactions to improve efficiency. In everything we do, sustainability comes first. Our entry into the Sustainable Aviation Competition takes a deep look into the future for aerospace vehicles, theorising how we can achieve zero-emission flight within the next decade. This is the future of propulsion.
So the aviation industry is increasingly becoming a leading contributor to global warming. Whilst other sectors such as energy, farming and manufacturing are making steps to reduce their greenhouse gas emissions, air travel is currently lagging behind. The industry has set targets to achieve net zero emissions by 2050, but currently it is some way from accomplishing this. In the last 5 years, battery electric vehicles have emerged as the focus of aviation's attempt to decarbonise. Rolls-Royce and Airbus have exhibited plans for their regional eFan-X in 2017, but this was later scrapped. Meanwhile, others have attempted to design larger electric aircraft or have made proposals for electrification of urban air mobility. But as of today, no electric aircraft operate commercially. As we have found in some of our previous design work, whilst all electric aircraft can operate with zero emissions, their low energy density because of the batteries compared to traditional aircraft fuel means that they are inherently heavy, which severely limits the range that they can achieve. But what if the requirements to incorporate a heavy battery into aircraft could be mitigated by making other parts of the aircraft lighter? Individually, we have developed some concept ideas for methods which may be able to achieve this.
While ideas such as lighter structural materials and more power-dense propulsion units are actively being considered by the industry today, our concepts envisioned a future where the increasing the efficiency of the airframe would radically reduce the weight of the aircraft. Traditional tube and wing aircraft such as the Airbus A320 exhibit a maximum lift-to-drag ratio of around 18. Our most aerodynamically efficient concept, a blended wing body aircraft or BWB, would exhibit a lift-to-drag ratio of up to 25. Therefore, a BWB would provide a greater lifting capacity than similar-sized tube and wing aircraft, which could be used to carry a larger battery pack. This is the concept we decided to take forward. During concept selection, we also disregarded ideas based on more radical zero-emission solutions like hydrogen or light-than-air technology, since the groundwork for battery electric flight has already been laid by the automotive industry and aerospace players in the last 5 years. We believe battery power is the future of propulsion.
From the concept designs, we decided to use distributed ducted fans for their high propulsive efficiency and effectiveness when integrated with a blended wing body design. This is due to their ability to provide a blown elevon effect, where the ducted fans act to re-energise the boundary layer at the elevons and enable greater aerodynamic performance. This is through allowing higher angles of attack before reaching the stall condition of the aerofoil, thus allowing for short takeoff and landing capability. To materialise the concepts into a CAD model, I used SolidWorks X Design. I started by sketching the overall plan profile of the BWB and sketching aerofoil profiles to fit within this. NACA 23012 aerofoils were chosen from research as a suitable section for the BWB. The profile was imported into XDesign as an image and sketched over as a spline profile. These profiles were lofted with guide curves from the plan view to form the BWB and wingtips. The mounts for the ducted fans were then modelled through an extrusion and the fans assembled accordingly. Elevons were then modelled and assembled into the model upon performing extrusion cuts and modelling the shafts. The ducted fans themselves were modelled in X Design and assembled within the ducted fan unit within CATIA.
This is our final aircraft design, featuring a frontal passenger cabin, ducted fans, wingtips and elevons. We created this render on the 3D Experience platform in CATIA Live Rendering, setting up lights and a camera path and using it to add the ELA decal. The next step was to subject our designs to some validation simulations.
So we wanted to simulate the flow of fluid over the blended wing body to really show off the efficiency of the body. And the first step was to import the model and then to assign the fluid region. We did this by creating a bounded box where the fluid would be and assigning the model as the fluid cavity. And then the next step was to assign our boundary and initial conditions. So how we did was that we set an inlet velocity condition and we set an outlet zero pressure condition, and then also assign the walls of the bounding box as the walls of the simulation with a slip condition. And then the next step was to assign the fluid as air and to create our output requests. So this would basically mean that the simulation would record the data we later wanted to use to create plots and figures. So before we could run the simulation and make an accurate simulation, we had to create a refined mesh. We did this by using the hex dominant mesh settings within Simulia and also using the boundary layer conditions to make sure that we had refined mesh at the edges to show the change in the boundary layer state.
We obtained the velocity fields from the CFD simulations and analysed the flow field around the blended wing body at different sections across the wing. By changing the domain to the blended wing body surface, we're able to obtain the general absolute pressure field across the blended wing body surface. We analysed pressure contours at different spans across the blended wing body and extracted numerical values for the pressure across the aerofoil. We plotted an XY path across the section of the aerofoil to obtain the pressures on the suction and pressure side of the aerofoil.
The next step was to add to the simulation by plotting velocity streamlines, and using the 3D Experience play button it was possible for us to easily animate the flow over the surface of the aircraft, as you can see in this video. We decided to show off this feature using the side view, the top view and an isometric view to really give a feel of how the flow passes over the aircraft body and generates lift.
From a historical XY plot of the different components of force, we obtained the drag and lift force as the solution came to convergence. These results, combined with those discussed previously, showed that the blended wing body wings and elevons must be mounted at a permanent angle in order to generate sufficient lift.
Our initial calculations showed that despite the advancements of the BWB structure, the low energy density battery technology would still limit our aircraft to operating on shorter regional routes. In an attempt to improve range, we built an analytical model of the power requirements for a typical regional aircraft flight. This power profile helped us identify that the takeoff and climb phases require significantly more power than the rest of the flight.
In order to give battery-powered flight the leg up it needs to reach the range required to service profitable regional routes, we decided to incorporate a beamed power solution. Beamed power refers to supplying power to the aircraft via electromagnetic radiation from a grounded source, reducing the need for the aircraft to carry its own stored energy in the form of batteries or fuel. While relying on beamed power for the whole flight would be unreasonable due to infrastructure requirements, providing beamed power during takeoff and climb phases would significantly increase the range of the aircraft by matching power drain during this time. A laser array would track photovoltaic cells on the underside of the aircraft with a combination of laser and photovoltaic chemistry chosen to match wavelengths for maximum conversion efficiency. A relatively brief time for the laser power transfer would mean that cooling would be a less serious issue than for the entirely laser-powered flight, as heat could be dissipated during the later phases of the flight. This use of beam power would help to improve the capabilities of battery-powered flight by reducing the reliance on battery energy density, which presently restricts electric aircraft to very short-range services. With this improved range, electric aircraft could replace those reliant on fossil fuels, flying higher passenger numbers on regional flights, and do this earlier than would be possible, relying solely on battery energy density improvements.
The management of our entry into the Sustainable Aviation competition was made simple and effective through use of the 3D Experience tools. We set up a project management tab on our team dashboard and used different apps to assist us in managing the project. Web Notes was useful for recording our meeting minutes from our daily morning and afternoon meetings on Discord. We were also able to record our goals for each day in these notes, so all team members knew what needed to be done next. This tab also included a quick link to our collaborative space and a 3D drive which we used to share documents we put together on research in different areas, as well as sharing screen recordings for the final video presentation. The most useful tool, however, was an Anovia project planner. We use this to build a Gantt chart of the tasks we need to accomplish to deliver the project goals. It was especially useful to assign these tasks to each team member. We also assigned a priority and put in input dependencies for each of the tasks. We used the deliverables and attachments feature to easily navigate to the output from the task. The summary tab gave us a good overview of our progress throughout the project, while the task tab was useful as a current to-do list.
When selecting materials to manufacture the aircraft, we wanted to achieve a lightweight solution with high strength, stiffness and damage tolerance, but also use materials that are inexpensive where possible. We considered the manufacturability, selecting suitable materials for parts that need to be 3D printed or machined. Reviewing the properties of common aerospace materials such as aluminium alloys, titanium alloys, ceramics and hybrid composites, we decided on a carbon and glass fibre reinforced plastic structure to enable us to design for a high structural safety factor whilst minimising weight. For certain heat sensitive areas on the aircraft, particularly surrounding the PV cells, titanium alloys will be used due to their high heat resistance as shown by the attribute charts which we analysed.
Our aftermarket considerations will maximise the number of components that can either be reused, recycled, or remanufactured at the end of the aircraft's life. To be reused, all parts will need to be awarded a certificate of airworthiness, so it's therefore important that thorough maintenance is carried out throughout the aircraft's life to keep parts in prime working conditions. So typically, a metallic aircraft component can be recycled by up to 90% of its mass. However, our aircraft will be built primarily with CFRP composites in order to minimise the weight. Composite components can be difficult to recycle. There are several ways to recycle composites now that we have been researching, though they are still developing and scaling up commercially. These include nitric acid treatment to dissolve the thermoset resins and incineration processes. Another sustainability challenge involved with our design is the end-of-life recycling of our batteries. So one suggestion is to sell on degraded batteries to ground-based industries who can accept a lower energy density rating. To preserve the quality of our aircraft components throughout its life, we will repair components where possible using advanced manufacturing techniques, further improving its sustainability. For example, direct energy deposition will be utilised to repair fan blades on the ducted fans if they become damaged during, for example, a bird strike. This is very important for our design given the increased number of fans in the distributed propulsion system.
When manufacturing the aircraft, our company will employ sustainable outsourcing, choosing ethical local partners to reduce the carbon cost of transportation. Waste will be minimised through additive manufacturing techniques as opposed to subtractive where possible, and overproduction will be avoided through the use of material resource planning and just-in-time techniques. Furthermore, the associated environmental risks with battery mines will also be tracked and appropriately managed where possible. This is the future propulsion from Team ELA, and we are calling it the Beamliner. Thanks very much for listening.